So here we have an energy calculation. Some of the key things to recognize here is that we've got a calorimeter, so that right away tells you that we've got to deal with energy. Calorimeter is simply the container in which this change is going to occur, and hopefully the calorimeter is sufficient in terms of insulating energy lost to outside of our system, which in this case is just a solution. When we have something like this, we want to look to see what's gaining energy and what's losing energy. So if we draw a little picture of what's happening here, so I'm going to put my beaker here, and actually the process that's occurring is fairly simple. We're just going to take potassium chloride and we're going to dissolve it in water. So we're going to end up with potassium ions and chloride ions dissolved in water. So we could represent this as KCl solid going to KCl aqueous. So it would be the physical change that is occurring. But again, there's an energy change associated with this. So let's take a look at what's happening to the mixture of this. Well, the solid and the water are both starting out at 24.2 degrees Celsius, and then the mixture is ending up at 21.1 degrees Celsius. So that solution overall is going down in temperature. So what we can do then is say that the Q lost is equal to the Q gained. And we've now identified that the thing that's losing the energy is what the temperature's going down is our solution. All right, if our solution lost energy, that means that the process, the dissolving itself, gained energy. And gained energy, that makes it an endothermic process. Okay, so now let's see what it wants us to figure out here. Well, we know the mass of the water that's in there. We know the mass of potassium chloride that we've dissolved. We know the temperatures of these things. And it wants us to calculate a couple of values. It wants us to calculate the number of joules per gram it takes to dissolve the potassium chloride and the number of kilojoules per mole that it takes. Well, hopefully we can see that, if we know the number of joules per gram, we can use a gram to mole conversion and a kilogram, a joule to kilojoule conversion to get to the kilojoules per mole. So let's kind of focus on this first one of getting the joules per gram. Well, we know the grams of potassium chloride that we dissolved. That's the 10.5 grams. So we need to figure out how much energy it took to dissolve that 10.5 grams. Well, we have this Q lost equals Q gained, and the dissolving is that 10.5 grams that dissolved. Now, so can we take a look, can we figure out how much energy the solution lost? Because then we would know the energy that was gained by the dissolving. And again, the energies are equivalent. One of them is going to be, calculation-wise, it's going to come out negative because energy lost is, we usually refer to it as a negative energy. All right, so let's take a look at that Q of the solution. If I do Q lost by the solution, because there's a temperature change associated there and there's a mass and a specific heat, I can use our mass times delta T times specific heat. The thing I want to remember is that this is for the solution. So this is lost for the solution. So I need to make sure that, the values I'm putting in there refer to the solution. Okay, so the mass of the solution is going to be the combined mass of both the water and the solid. So there's the 105 grams and the 10.5 grams. So we end up with 115.5 grams. The 0.5 part there probably isn't a significant digit, so we're going to have to kind of worry about that later. The delta T, final minus initial. So we ended up at 21.1. We started at 24.2. So the delta T is going to be negative 3.1 degrees Celsius. And then the problem tells us that we can use the specific heat for water for our solution. So that's 4.18 joules per gram degrees Celsius. And watching our units, which is always good practice. We can see that grams cancel with grams, degrees Celsius with degrees Celsius. We're left with joules for our energy unit, which is what we want to have present there. And so this is going to come out to 1,497 joules. That would be negative. Significant figure-wise, we really aren't going to be able to keep all of these because our delta T only had 2 significant figures, so we really only get to keep 2 there. So this would be negative 1,500 joules. Now, that's not the energy per gram. That's the energy for 10 grams, right? So if we're going to figure out the energy per gram, we're going to take that and divide by the 10.5. So let's go over here to the left a little bit. And this is also, remember, it's negative, so that was the energy that was lost by the solution. If we're going to look at the dissolving, that's energy gained, so that's going to be the positive of that. So we're going to have 1,500 joules gained by the process, by the dissolving, divided by the 10.5 grams that we dissolved. And so that's going to give us, let's see, so that will give us 140 joules per gram. And again, if we want to, at this point then to get the kilojoules per mole, we're just going to do conversion factors. So we would change the joules to kilojoules. So 1 kilojoule is 1,000 joules. And then the grams to moles, so grams to moles. And again, just kind of watch my units as I go along, make sure things cancel out. The molar mass for potassium chloride, 1 mole is going to be 74.5 grams. So if I do my math, I get 10.4 kilojoules per mole. Significant figures, I'm probably at where I should only have 2. So I can do 10 with a point kilojoules per mole. Or I can do 1 times 10 kilojoules per mole. So there are my 2 values for the energy per gram. And again, what makes a problem like this difficult is that we can do this part here, this Q lost for the solution. We've done that before. The key is putting the 2 things together, recognizing that there's something losing energy, something gaining energy, and then what do you do to calculate each part there and putting that together. So this is one of those kind of typical, each individual part's not all that bad, but putting it all together is what could potentially give us a hard time.